Hello, everyone. In this episode, I would like to talk about analytical polylambda CDM dynamics. So you see, we have plenty theories out there, and we have plenty observation, telescopes, colliders, and we try to understand by mapping our theoretical models into observational data, nature at a deeper level. And how do we do that? Using advanced mathematics. So let's see. In cosmology, we study the universe in what we call cosmological gravitology. And we describe every system of our universe using this equation that you can see there in blue. Basically, don't get intimidated by this equation because we can simplify this equation by saying that the action, which is the S, is equal to the geometry times the energy. So this complicated, sophisticated equation is simplified to a simple terms, an action. When we act, we use energy and geometry, and we use that in order to describe all the universe around us. So now let's see. At the heart of this theory, there is general relativity, Einstein's unique theory of massless gravity. And this is a basic theory that has passed many tests. However, we extend this theory in multiple ways. We break some assumptions, we add a field, or we add a massive gravity. And you see here, we can color code all these different type of theories. For example, when we add a field, we can add different type of fields, and these have different flavors, different name of people that they have been working on, and extending of those things. And when we break the assumptions, what do we break? We break isotropy and homogeneity, locality and causality. So maybe we can add extra dimensions or probabilistic dimensions, or we can even talk about different types of geometries. But there are so many technical terms you see in this picture. However, what do you notice? That we can color code them, and each color represents something from this unique equation there. So all this red part, and there's also, oops, I forgot one more term, the fat theories. So you see, the red part models this part of the equation. Every breaking assumption that we do is most probably related to geometry. While if we add fields or massive fields, we talk about energy. Now there is an additional theory, the fat theory, that we change what we call the action. It acts at different ways. Now, how we can distinguish among all those different theories or combinations of those theories, which one of them corresponds better to our observation? Therefore, my collaborator Jackson Levi-Said and I, we have been studying for some time now some quintessence model, and then we found one more model that answers to the following question. Is there an effective model to distinguish among different modified gravity cosmological models? And it turns out the answer is yes. And this is what we call analytical polylambda CDM dynamics. Let's see what is that. Basically, in the standard model of cosmology, the universe is filled with baryonic visible matter at 1%, cold dark matter at 31%, and dark energy at 68%. Cold dark matter is CDM, dark energy is modeled with a lambda, the cosmological constant, and if we combine them together, we get the lambda CDM model that describes the standard model of cosmology as we know it. However, in this analytical polylambda CDM model, we have the same basic components, baryonic matter and cold dark matter. We also have dark energy, but now at about less, 67%, which is modeled by lambda, and we add some different flavors of this modified gravity that I discussed before. And we can call them with different mathematical letters, which are basically poly letters. Poly in Greek means a lot, much. And since we add a lot of flavors of this modified gravity model, we call this model poly lambda CDM, and hence the name. So maybe all this sounds a bit technical, but what analytical polylambda CDM cosmology tells us? It tells us that we find that there is an interplay among different flavors of modified gravity theories. And what does that mean? That all these theories interact with each other, and we can use them in order to model observational data. Therefore, the next step is to try and see different flavors of this model and feed them to the data and see which one of them describes better reality. Thank you very much for your attention. If you like it, subscribe to support art and science. Happy cosmologing, everyone!